session. We first complete the remaining parts of the lecture in half an hour and then continue with the tutorial session for an hour. In the first two lectures, we have studied the preliminaries, basic properties of numerical range, convexity of numerical range, boundary point, sharp point, and normal eigenvalues. One property, namely unitarily invariance property, says that the numerical range of two unitarily similar matrices are same. We here study that converse is true for n is equal to 2. That is, if numerical range of two 2 by 2 matrices are same, then they are unitarily similar. For this, we need this first lemma. Let A belongs to M2. That is, A is 2 by 2 matrix with complex entries. A is unitarily similar to an upper triangular matrix of this form, where alpha A is non-negative. Second, we need this second property to prove our next theorem. Let A be belonging to M2 have same eigenvalues. Eigenvalues are same and trace A star A is same as trace B star B. Then A and B are unitarily similar. Now to prove this first part, we use short triangularization theorem. By short triangularization theorem, every square matrix is unitarily similar to this upper triangular matrix, where lambda 1 and lambda 2 are eigenvalues of A. Now, alpha A may be any number, positive, real, or complex number. We have to show that we can choose here alpha A to be a non-negative number. Now, if this alpha A is already positive, then it is okay. Otherwise, this we take this unitarily similar to lambda 1 0, lambda 2 beta A. Beta A is complex. Now again choose this unitary 1 exponential iota theta 0 0. And now multiply with this, we see that these calculations gives that A is then unitarily similar to this matrix. Lambda 1, lambda 2, here exponential iota theta beta A. Now this is true for any theta belongs to R. Now if a complex number is given, then we can multiply it with another complex number such that the product is real. So we choose theta such that this is real. So this matrix A is unitarily similar to this matrix, where alpha A is real. If it is non-negative, the lemma, the first part of the lemma is proved. If it is negative, then again we choose this unitary 1 0 0 minus 1. Then this matrix is unitarily similar to lambda 1 0 lambda and minus alpha. So if alpha A is negative, we can take minus alpha. So ultimately we have alpha A is non-negative. Now we prove second part on using this first part. By part 1, there exists a unitary U such that U star AU is equal to lambda 1 lambda 2 0 alpha A. Alpha A is non-negative. Similarly, we can choose unitary V such that V star B is this, where alpha B is non-negative. Now eigenvalues are same. Eigenvalues of A and B are same. Now we have show that alpha A is equal to alpha B when trace A star is equal to trace B star. Now trace is similarity invariant. Therefore, we can write trace A star A as trace U star A star U. In between this, we put UU star because this is identity. Then this gives trace U star AU star U star AU. Now from 2, that is from here, we calculate its square U star AU star, then U star AU. This comes out to be this matrix. So trace of this matrix is mod lambda 1 square plus mod lambda 2 square plus mod alpha A square. And by force, since trace of A star A is equal to trace U star AU star U star AU, therefore this trace A star A is mod lambda 1 square plus mod lambda 2 square plus mod alpha A square. Similarly, we can do the same for trace B star B, which comes out to be mod lambda 1 square plus mod lambda 2 square plus mod alpha B square. Now, given that trace A star A is equal to trace B star B. So, equating these two expressions, we have alpha A square is equal to alpha B square. And this gives alpha A is equal to alpha B, because we have already shown that alpha A and alpha B are non-negative. So this means U star AU is equal to V star BU. Now, from this on multiplying here in left by U and right by U star, we have A comes out to be this. And since product of unitary is unitary, A is equal to U1 star BU1. So A and B are unitarily similar matrices. Now we prove this main result. A and B are matrices of order 2. Then A and B are unitarily similar if and only if their numerical ranges are same. We have already discussed that if A and B are unitarily similar, then their numerical range are same. We have to discuss now the converse part. Now suppose numerical range of A and B are same. And if numerical range of A and B are same, both are ellipse and they may be degenerate or non-degenerate ellipse. So their foci are also equal because they are same ellipse, and eigenvalues lie on the foci of the ellipse. So their eigenvalues are equal. This means trace A is same as trace B. Now we take this matrix X A minus trace A by 2i and Y B minus trace B by 2i, and this is equal to B minus trace A by 2i. Why? Because trace B is same as trace A. Also note that eigenvalues of A and B are same. Therefore, eigenvalues of X and this Y are also same. Why? Because we are just subtracting trace A by 2 from both the matrices. Now, since numerical range of A and B are same, therefore length of major axis of W and WA are equal. And we have length of major axis is this expression, trace X star X plus 2 determinant X power half. And similarly in right hand side. Since eigenvalues of X and Y are same, therefore their determinant are same. So squaring both sides, this 2 determinant X cancel with 2 determinant Y. So from here we have trace X star X is equal to trace Y star Y. Now substitute value of X and Y from here. We get this expression, and on simplifying this, we find that trace A star A is equal to trace B star B. So if numerical range of two matrices are same, then their eigenvalues are same, and also trace A star A is equal to trace B star B. So if numerical range of 2 by 2 matrices are same, then they are unitarily similar by last lemma. Now, the numerical range is a compact subset of complex plane. It is bounded, therefore its size is important. Its size is measured in two ways: one, numerical radius, and second, diameter of numerical range. The diameter of numerical range we will study tomorrow in connection with linear maps. Here we study numerical radius. The numerical radius is the radius of the smallest disk centered at origin, which contains the numerical range. That is why it is numerical radius. Or we can define it as R is equal to maximum mod Z. Z belongs to numerical range of A. Now, we first find an upper bound for this numerical radius. This is due to Hirsch 1902. And in next theorem, we discuss an improvement of this result. Let A is equal to Aij belongs to Mn, then numerical radius this is less than equal to n time maximum of mod Aij. This is very simple. bound. And once we have bound upper bound for this numerical radius, we also have this upper bound for modulus of the eigen values, any eigen value. Why? Because eigen values also lie in numerical range. Now proof goes like this: take x unit vector, then x belongs to WA, therefore mod x star AX this equal mod. We calculate these entries of AR AIJ. Now using triangle inequality, this less than equal to sum mod ij mod xi mod xj. Now we can replace this by maximum. Then again we have this inequality here. Maximum ij this outside mod aij, sum ij mod xi mod xj. Now note that this is just mod sum mod xi whole square. Why? We can write this as sum I12 and mod xi square plus sum I not equal to j mod xi mod xj. And this is just twice sum I less than j mod xi mod xj. So this equal maximum ij mod aij and this sum mod xi whole square. Now we use Cauchy-Schwarz inequality to show that this is less than equal to n. Cauchy-Schwarz inequality says this: sum mod xi square, sum mod yi square greater than equal to sum mod xi yi whole square. Now take each yi to be 1. Then from this relation, sum mod xi whole square is this. If each y is 1, this comes out to be n. So sum mod xi whole square less than equal to n sum mod xi square, and this is just n x star x. X star x is 1, x is unit vector, so this is n. So from this inequality we get mod x star ax is less than equal to n, maximum of mod aij. Now next we discuss an improvement of this result last. For this we begin with Gauss-Gorin disk theorem. The Gauss-Gorin disk theorem says that we first define if A is equal to Aij is n by n matrix, then Ri dash defined as sum j1 to n j not equal to I mod Aij. This means we are adding the off diagonal entries of the ith row except diagonal entry, and it is also called deleted absolute row sum. Likewise, this Ci dash is sum j1 to n j not equal to I mod Aj I. That is, here we are adding off diagonal entries of ith column except the ith diagonal entry, and this is called deleted absolute column sum of A. Then Gauss-Gorin disk theorem says that spectrum of A, that is all eigenvalues, lie in the union of these n disks. These n disks centered at AII, radius Ri dash A, and also they lie in this region, union of these n disks centered at AII and radius Ci dash A. In the next theorem, we discuss that numerical range of A is also contained in some Gauss-Gorin type region. For this, we define this GIA as half average of absolute deleted row sum plus absolute deleted column sum, and consider this set GWA. This is convex hull of union of all the disks centered at AII and radius GIA. Now note that in Gauss-Gorin disk theorem, center is AII. Also here we have taken these disks and disks, but center is here AII, but radius is GIA. That is average of RA dash A and CI dash A. Also, in case of Gauss-Gorin disk theorem, the region may or may not be convex. But here it is convex hull of this set, therefore this is always a convex set. That is, in this, if the disks are disjoints and Gaussian region is not convex, but here it is always convex. Now we first prove this theorem. If A belongs to Mn, numerical range of A is contained in GWA. What is GWA? Convex hull of union of all these disks centered at AII and radius GIA, where we have defined GA like this. We prove this theorem in 3 steps. First, to show that this set is contained in GWA. We show that if alpha is a complex number, and suppose alpha does not belong to this set, then alpha also does not belong to WA. And this will give WA is subset of GWA. Now, to show this, we first prove that if GWA is in right half plane, then numerical range is also in right half plane. To show numerical range is in right half plane, we have just to show that its real part is in right half plane, because a complex number is in right half plane when its real part is in right half plane. And by projection property, a real part of numerical range of A is numerical range of A plus A star by 2. So it is sufficient to show that numerical range of A plus A star by 2 is contained in right half plane. Now this GWA is contained in right half plane. This means all these disks are contained in right half plane. And then these interval x minus real part of AII mod less than equal to GIA, they are also in right half plane. What we are discussing, this disk is in right half plane. So real part of AII is here on real axis. Then real part of AII minus GIA, this interval, and real part of AII plus GIA up to here. This also contained in right half plane. Now we consider this matrix A plus A star by 2 and write it as B. Entries of Bij, then Aij plus Aj, I conjugate by 2. So diagonal entries are real part of AII. And as shown in figure, this interval x minus BII. BII is real part of AII. This is less than equal to this. This is Gaussian disk. X mod x minus real part AII less than equal to half mod of this. Now by triangle inequality, this part is less than equal to half sum mod Aij plus mod Ji bar, and this is GIA. So what we have, the numerical range of A plus A star by 2 is contained somewhere here. Why? Because eigenvalues are contained in Gaussian disk, and therefore eigenvalues of Hermitian matrix are contained in this interval, which is in right half plane. So A plus A star is A by 2 is a Hermitian matrix. So this numerical range of this is also contained in right half plane. Now, second, we show that if 0 does not belong to GWA, then 0 also does not belong to numerical range of A. Suppose 0 does not belong to GWA. Since GWA is convex, we can rotate GWA about origin so as to bring it in the right half. This means for some theta, we have GW exponential iota theta A is in right half plane. Since GW of this matrix is in right half plane, then as discussed above, numerical range of exponential iota theta is in right half plane. Also, right half plane means this open right half plane, that is excluding imaginary axis. So it does not contain origin. 0 does not belong to, therefore, if numerical range of exponential iota theta, which is biscalar multiplication property equal to exponential iota theta WA. So this implies 0 also does not belong to WA, because if 0 will belong to this WA, then on multiplying with this, we get that 0 also belongs to numerical range of exponential iota theta A. Finally, we show that if alpha does not belong to GWA, then alpha does not belong to WA. Now this GWA plus beta AI also satisfies translation property. That is, this are just translated as a centers are translated to some new position with factor this beta. So this GWA also satisfy translation property. Now suppose alpha does not belong to GWA. Then by this translation property, 0 does not belongs to GW of A minus alpha. Then as shown above, 0 does not belong to numerical range of A minus alpha I. This implies alpha does not belong to numerical range of A. Hence, we conclude that numerical range of A is contained in GWA. And what is the use of this? We use this to derive our next inequality. And this is the improvement over the result of Hirish. Let Aij belonging to Mn, then this numerical radius is less than equal to maximum I12 and half sum J12 and mod Aij plus mod Aj. As we have discussed, above, numerical range of A is contained in the convex hull of the union of these n disks. So consider this disk mod Z minus A less than equal to R, centered at A, radius R. By triangular inequality, mod Z minus A is greater than equal to mod Z minus mod A, then this is less than equal to R. So mod Z is less than equal to R plus mod A. This means that disk mod Z minus A less than equal to R is contained in the disk mod Z less than equal to R plus mod A. We also note this is the disk centered at A and radius R. So this is at a distance mod A. So if we take this to be radius R plus mod A, then this disk is contained in this outside disk with center origin and radius R plus mod A. So it is clear that these end disks are contained in these end disks centered at the origin. So we can write here in right hand side, we can take their maximum. Then all the disks, these disks are contained in this disk centered at origin, and in right hand side maximum of these. So mod Z is less than equal to maximum of I mod AII plus GIA. Since this is a disk, this is a convex set and therefore contain union of all these disks. Therefore, we must have mod Z less than equal to maximum mod AII plus GIA. Now here just substitute value of GIA and this simple calculation finally gives the main result. Now at last we give some idea of real numerical range. This is not so useful much in application, but we should know what is real numerical range. Let A belonging to Mn be a real matrix. Matrices are taken real, and WRA is defined as XTAX. X belongs to Rn. X is also here real vector, and X transpose X is 1. This is called the real numerical range of A. A itself is a real matrix, that is all the entries are real. Since all the entries are real, X is also a real vector. So numerical range lies on real axis. Second, if A is a real symmetric matrix, then WRA is a line segment on real axis joining smallest and largest eigenvalues of A. Let A be real symmetric matrix, then we have this real orthogonal matrix Q such that Q2AQ is diagonal matrix. So from this we can write A is equal to multiply here with Q and here Q transpose. A is written in this form. Now take this expression XTAX. This comes out to be XT and write A between here. So if we put this equal Y, then we have Y transpose Y. So again we get this expression. And this comes out to be convex combination of lambda 1, lambda 2, lambda n, and eigenvalues of real symmetric matrix are all real. So WRA is then line segment joining the smallest and largest eigenvalue of A. It may also be noted here that if A is a real symmetric matrix, then following conditions are equivalent. U star AU is real for all U belongs to Rn. Z star AZ is real for all Z belongs to Cn. It is clear that 2 implies 1, because if 2 is true for all complex number, this is also true for real number. 1 also implies 2. Take Z to be x plus iota y. X and y are now real vectors belonging to Cn. Then Z star AZ is x star minus iota y star Ax plus iota y. This equal x star Ax plus iota x star Ay minus iota y star Ax plus y star Ay. Now note that this can be written as x star A star y star. But A is real symmetric. Therefore, A star is same as A. Now this is a number and this is real. So ultimately this cancels out with this. So this equal x star Ax, y star Ay. These two both are real. Therefore, this is a real expression number. Now, real numerical range of A is equal to real numerical range of A plus A transpose by 2, which is equal to numerical range. In last, we have numerical range, that is X may belongs to Cn. This is so why, because X transpose of A plus A transpose by 2X, this is an element of this. WR A plus A transpose by 2. This equal half XT AX plus XT ATX. And since this is a single number, we can write this equal to its transpose. So we have these two expressions, which is same as XT AX. So a real numerical range of A is equal to real numerical range of A plus A star by 2. So ultimately, if we have to study real numerical range, we have just to study the numerical range of this real symmetric matrix. Also, this real numerical range of A plus A star by 2 and A plus A transpose by 2, as we have studied, are both line segment joining smallest and largest eigenvalue. So therefore, WR of this is same as W of A plus A transpose by 2. Also, all the real eigenvalues of a real matrix A are contained in WRA. Why? If an eigenvalue is real and matrix is real, then there always exists real eigenvector. So Ax is equal to lambda x. Take this x transpose Ax, this lambda xtx. This comes out to be lambda. So lambda belongs to numerical range of A. It is also clear that WRA is a convex set. Why? Because WRA is same as WR of A plus A transpose by 2. And this is same as numerical range of A plus A transpose by 2. Hence WRA is convex. Now let A belonging to Mn be a real matrix. Then WA is equal to WRA if and only if A is symmetric, that is real symmetric. If A is real and symmetric, then WRA and WA are both line segment joining smallest and largest eigenvalue. So WRA is same as WA. Conversely, let A belongs to Mn be real and numerical range of A and real numerical range of A are equal. Then WRA and hence WA is a line segment on real axis. And this we have discussed in first talk that WA is a line segment if and only if A is Hermitian. But here it is given that entries are real. So A is real symmetric matrix. Now we come to tutorial session. Because in the first day, we have taken first lecture and then second lecture of 1 hour. So we have completed this half an hour. Now we go to tutorial. We have uploaded the tutorial in Dropbox. So I think you have solved some of these questions. Yeah, this is first question. Show that if A belonging to Mn has real entries, then numerical range is symmetric with respect to real axis. Yes, anyone want to comment? Symmetric with respect to real axis, that as it is above real axis, those so mirror image is below real axis. Likewise here or any other figure, but symmetric with respect to real axis. This is very simple. Anybody want to comment on this question?
If alpha plus I to WA, then alpha minus I beta is also in WA. We have to prove that. For this, if alpha plus I beta equal to some x star AX, then if we take x bar vector, then x bar AX star is A alpha minus I beta, which is
Yes, good. So we express it here. If we have to show that this is a region in complex plane is symmetric about real axis, we just have to show that if Z belongs to numerical range, then its complex conjugate also belongs to numerical range. Suppose Z belongs to numerical range, then Z is x star AX. For some unit vector x belongs to Cn. Then this Z conjugate is x star AX conjugate. This x star AX star. And this equal x star A star X. A star is just A transpose as A is real matrix. Again, this is a number, we can take its transpose. And this comes out to be X transpose here due to this. And this X transpose conjugate, which is X conjugate. Now we put X star, X bar is equal to Y. Then X transpose is Y star. So this is equal to Y star AY. So this also belongs to numerical range. Hence, numerical range is symmetrical about real axis whenever entries of A are real. Now we have just discussed that numerical, if numerical range of 2 by 2 unitarily similar matrices are same. This is true for n by n. Then if two matrices are unitarily similar, then their numerical ranges are same. Conversely, if numerical ranges are same, then for 2 by 2 matrices, they are unitarily similar. That we have proved in this talk. Now, here show that two matrices of the same size and having same numerical range need not be unitarily similar. This means we need a counter example when n is greater than equal to 3, because when n is equal to 2, this always holds. Yes, anybody want to comment? Anybody want to comment? No? Yeah, this is simple. Take these two diagonal matrices. A, 1, 3, 4 diagonal entries, and here diagonal entries are 1, 2, 4. What is the numerical range of A? Yes, numerical range of A when A is diagonal.
Eigenvalues of A.
Yes, convex hull of the eigenvalues of A. So this is just line segment joining 1 to 4. And this is matrix B. Its eigenvalues are 1 to 4. So again, convex hull of the eigenvalues of 1 to 4. So this again comes out to be 1 to 4. So both these matrices have same numerical range. But are they similar? A and B are similar matrices or not?
No.
No, sir.
Why?
Because
Because
they
they
don't
are
have same eigenvalues.
same eigenvalue, but they are not similar and hence they are not unitarily similar also. Clear, numerical ranges are same, but they are not unitarily similar. So we have two matrices of the same size and having same numerical range need not be unitarily similar. And this is true when n is greater than or equal to 3. Now this third question, let Aij belongs to Mn. Then all the diagonal entries are in numerical range of A. Yes, anybody want to comment?
Sir, if we take
Yes,
x is
sir.
equal to ei, that is the one of the vector in standard basis of Cn, then x star ax is equal to aii.
Yes, good. For the first part, we note this Aij. We take x to be this vector. First entry is 1 and all other entries are 0. And then calculate this x star ax. 1, 0, 0, so on. Here 1, 0, 0. This matrix, when we calculate, this comes out to be here just A11, then A from here A12, from here A1n. And this is equal to A11. So x star ax is in numerical range, so A11 is in numerical range. Likewise, if we choose x is equal to ek, that is this type of vector where kth entry is 1 and all other entries are 0, then x star ax comes out to be akk. So akk belongs to numerical range. Yes, second part, trace A by n belongs to numerical range.
All
Yes,
eigenvalues A belongs to WA.
yes,
So the convex of this content in WA. And if we choose 1 by n as constant, 1 by n lambda 1 plus 1 by n lambda 2 plus dot dot 1 by n lambda n, this is also belongs to WA.
yes, good. We have, either we can argue from the eigenvalues or from the diagonal entries. WA numerical range is a convex set. So any convex combination of AIIs, that is point in convex set, this is also in numerical range. We take each P1, P2, Pn is equal to 1 by n. Then this sum Pi Aii is equal to 1 by n, sum this trace A, so this equal trace A by n. So this trace of A by n is in numerical range. Now this third part,
So we will take the vector with all entries 1 by n, 1 by root n.
1 by root n, and then inside 1, 1, 1. Okay.
Yes, sir. Saying
Yes,
all
good.
entries 1 by root n.
Okay. Let x is equal to 1 by root n, 1, 1, 1 transpose. Then x belongs to Cn. Also in this case, x star ax comes out to be 1 by n sum ij a ij. Why? For example, take this 3 by 3 matrix. Then 1 by root 3, root 3, this is 1 by 3, this 1, 1, 1, 1, 1, 1. When we multiply with this, we get this part. And when we multiply by this part, we have all the entries are add up.